Welcome to the deep dive. Today we're taking a truly monumental stack of sources and boiling it all down.
Into a single knowledge sprint, yeah.
Exactly. Our mission is to absorb the core foundational ideas and the really advanced techniques that are driving modern machine learning today. We're going from the basics, data cleanup, all the way to the big stuff.
All the way to the architectures behind today's large language models.
That's right.
So this is the roadmap.
This is the comprehensive roadmap. We've pulled together everything that covers the entire life cycle of building an ML system.
Yeah.
We'll touch on basic terms, Python specifics with PyTorch, and even bring in some key insights from researchers like Benjamin Kaufman on graph neural networks or Zhixian Zhao on large-scale models.
Okay, let's unpack that roadmap right away. Building any kind of system needs structure. The sources all seem to agree on three core non-negotiable phases in the machine learning workflow. What are we looking at?
They're sequential, and they are absolutely crucial. So phase one is pre-processing.
The unglamorous part. The very unglamorous but necessary work of getting your raw data into a shape you can actually use. Phase two is training and selecting a model.
Choosing the right tool for the job.
Right. And then the final phase is evaluating that model and, finally using it to predict on new data you've never seen before.
That sets the table perfectly. And the classic starting point for all of this is supervised learning. This is where you have labeled data, you already know the right answers.
Yeah.
It seems to have two main jobs in the ML universe, right?
It does. It generally breaks down into classification and regression. So classification is all about predicting discrete categories, labels.
Like sorting mail.
Exactly. Is this email spam or not spam? You get a hard categorical answer.
And regression.
Regression is for predicting continuous values, a number. So if you're trying to predict the price of a house or maybe tomorrow's temperature, you're in the world of regression.
There was a great visualization for classification we saw. 30 data points, 15 of class A, 15 of class B, plotted on a graph with two features, 6 EN9 tower and 6 TN towers. And the whole goal is for the algorithm to learn that perfect dividing line.
That decision boundary, yep. And if you start with the simplest possible boundary, just a straight line, you land on a foundational model called logistic regression.
Okay, now this model is critical, but the name is a bit confusing, isn't it? It has regression in the name, but it's used for classification.
It is confusing. And that's because, under the hood, it is a linear model. The magic is in the sigmoid function.
The activation function.
Right. So the model calculates a linear score based on the inputs and their weights. But then, before it gives you an output, it shoves that score through the sigmoid function.
And that squashes the result into a probability.
Precisely. A number between 0 and 1. And to find the best weights to do that, the model goes through an optimization process, maximizing what's called the log likelihood function. It's just a fancy way of saying it finds the weights that make the predicted probabilities line up best with the actual labels in the data.
So training a model requires clean numbers, which means we have to talk about step one, pre-processing. The sources just hammered this point home again and again. This stage can make or break your entire project.
It's the truth nobody wants to talk about. And let's start with the most common problem, missing data. You'll see it as NaN in your table.
So what do? Just delete the row.
You can. You can either eliminate the examples or features or, and this is more common, you impute them.
Imputation.
Yeah.
So guessing the missing value, the simplest way I've mentioned was mean imputation, right? Just fill in the blank with the average of that whole column.
Exactly. It's a quick fix. Then you have to deal with your categorical data. And you have to distinguish between data where order matters. We call those ordinal features.
Like t-shirt sizes. Small, medium, large.
Perfect example. ML, XL. You can just map those to 1, 2, 3. But then you have nominal features like colors, red, blue, green, where there's no inherent order.
And you can't just map those to 1, 2, 3 because the model might think 3 is somehow more important or bigger than 1, which makes no sense for a color.
Precisely. For those nominal features, you have to use one-hot encoding.
I think of this as creating a little binary checklist. So if your column is color, you make new columns. Is red, is blue, is green.
And for any given row, only one of those can get a 1B hot and the rest are 0. It's a perfect description.
Okay, here's a huge point in data prep. Feature scaling. Why do we bother standardizing features to have, say, 0 mean and unit variance? It just sounds like a lot of extra math.
It sounds like extra math, but it is absolutely essential for optimization. See, most learning algorithms, especially the ones based on gradient descent like logistic regression or neural networks, they don't understand the scale of your features.
They just see numbers.
They just see numbers. So if one feature is on a scale from 0 to 1 and another goes from 0 to 10,000, the algorithm will think the huge feature is way more important. Its updates will be completely skewed. Scaling puts every feature on a level playing field.
It helps the algorithm find the best solution faster and more reliably. But the sources highlighted a really important exception here, which I think is a must-know.
Yes, this is crucial. Decision trees and random forests are scale invariant
Why is that?
because they work by asking questions about thresholds. Is the value of feature X greater than 5? It doesn't matter if that feature was scaled or not. The answer to the question is the same. The split happens in the same place.
So if you're using a tree-based model, you can just skip scaling entirely.
You can, and that's a huge design choice that can save you a ton of time.
Okay, sticking with features, what about when we have too many? We get into feature reduction.
Yeah.
I mean, why would you ever throw away data that might have information?
For efficiency and for noise reduction. Less data means less storage, faster algorithms. But the really important part is that if your data set has a low signal-to-noise ratio, tons of irrelevant features, getting rid of them can actually improve your model's performance.
It helps a model focus on what's important.
Exactly. Now, there are two ways to do this. You can do feature selection or feature extraction.
Okay, so feature selection sounds straightforward. You just pick the best of your original features. But feature extraction creates brand new features that are less interpretable. Why would we ever do that?
That is the core trade-off. With feature selection, you keep the original meaning. You can look at the model and say, okay, feature number 5 was important. But with feature extraction, using a tool like PCA Principal Component Analysis, you create new features that are combinations of the old ones.
So you lose that direct interpretability.
You do. But what you gain is often a much more powerful compression of the information. PCA finds the directions in your data with the most variance, so you can often capture most of the signal in far fewer dimensions. It's clarity versus compression power.
Well put. And that idea of trade-offs brings us perfectly to model selection and the famous no free lunch theorem.
Ah, yes. The theorem is basically a humility check. It just says that no single classifier, no single algorithm works best for every single problem.
You can't just say a decision tree is always better than logistic regression.
Never. You have to try different things. You have to compare performance on your specific data. If you don't, you're probably leaving performance on the table.
So let's look at a couple other models. Decision trees are really popular because they are so interpretable.
Right. They're like a flowchart, a series of if this, then that questions. But what's their big downside?
They can overfit like crazy. If you let a tree get too deep, it just ends up memorizing the training data, noise and all, and then it fails on new data.
Exactly. Now, you can contrast that with something like K nearest neighbors, or KNN.
Which is called a lazy learning algorithm.
It's lazy because it does almost nothing during training. It just memorizes the entire training data set. Then, at prediction time, when it sees a new point, it looks at the closest points from its memory and takes a vote.
And because it relies on the idea of closeness, it's super sensitive to feature scaling, isn't it?
Extremely. It often uses Euclidean distance, so a feature with a huge scale will totally dominate that distance metric. And the other issue is that at prediction time, it has to compare the new point to every single point in memory, which can get really slow.
Okay, so we've got our candidate models. Now we need to test them properly. The standard practice is to split the data, say 70% for training, 30% for testing. But just using that 30% test set over and over is a bad idea.
It's a very bad idea. It's called data peaking. If you try 10 models, pick the best one based on that single test set, and then report that score. Your score is going to be optimistically biased. You've accidentally tuned your model choice to the quirks of that specific test set.
So the better solution is nested cross-validation.
This is the robust gold standard solution. You have an outer loop that you use only to get your final performance estimate, the real score. And then you have an inner loop that you use to do all your tuning and model selection.
It's like keeping the final exam sealed until after you've taken all your practice tests.
Perfect analogy. That's exactly it.
And when we evaluate, simple accuracy, correct predictions out of total predictions, can be misleading, especially with imbalanced classes like, say, diagnosing a rare disease.
For that, you need the confusion matrix.
It breaks down the errors.
It shows you your true positives, your false negatives, everything. That lets you calculate metrics that really matter, like precision and recall.
In a medical diagnosis, which one is more important?
Well, if we're looking for tumors, recall is almost always paramount. Recall asks, of all the people who actually had a tumor, how many did our model find? A false negative missing a tumor is a catastrophic error. You'd rather have more false alarms or false positives than miss a real case.
The matrix forces you to think about those real-world consequences. Okay, let's pivot to the modern powerhouses. Neural networks and deep learning. The basic unit, the neuron, it's actually pretty simple.
It really is. The original idea from McCulloch and Pitts was just a simple logic gate. Signals come in, they get added up, and if they cross a threshold, the neuron fires. That simple idea is the building block for everything that follows.
And when you stack these into deep networks with millions or billions of parameters, how on earth do you train them?
The answer is backpropagation. Conceptually, it's just a very clever and efficient application of the chain rule from calculus. It's a way to figure out how much each individual weight in the network contributed to the final error and then adjust it accordingly.
But with so many dimensions, the loss surface must be incredibly complex. It seems easy to get trapped in a valley that isn't the deepest one.
That's the problem of local minima, exactly. And if you use traditional gradient descent, which looks at the entire dataset for every step, it's like a very cautious hiker. It moves slowly and can easily get stuck in the first valley it finds.
This is where the noisy updates of stochastic gradient descent become a feature, not a bug.
Exactly. Stochastic gradient descent, or SGD, takes updates based on tiny samples, maybe even just one example. This makes the path down the mountain much noisier and more erratic, but that noise is actually good. It can jolt the algorithm out of those shallow local minima.
And then there's mini-batch GD.
Which is the compromise. It uses small batches of data, so you get some of that beneficial noise, but you can also use vectorized hardware for much faster computations. It's the sweet spot.
To build these networks, you need specialized tools. The source is pointed to PyTorch.
Yes, PyTorch is a key open source library. It gives you all the building blocks you need, like tensors, which are optimized multidimensional arrays, and the torch.nn module for defining layers. It makes building these complex architectures much more manageable.
Let's talk about the flagship application, natural language processing. We've gone from simple bag-of-words models to a world completely dominated by transformers, BERT, GPT, and so on.
The transformer architecture was a revolution, and it's based on this incredibly powerful two-stage process. The first stage is unsupervised pre-training.
Unsupervised, so no labels. How does a model learn from just raw text?
By doing simple, self-supervised tasks on a massive scale. You feed it, a huge chunk of the internet. A model like GPT learns by trying to predict the next word in a sentence. A model like BERT learns by having words randomly masked or hidden, and it has to predict what they were.
So it learns grammar, context, and facts about the world just by doing that.
It builds this incredible general-purpose knowledge of language, and then comes stage 2. That's when you take that huge pre-trained model and you adapt it for your specific labeled task, like classifying movie reviews. And you only need a relatively small labeled data set to do it. It's a very efficient form of transfer learning.
Could you quickly break down the difference between, say, GPT and BERT? They seem to have different strengths.
A simple way to think about it is this. BERT is an encoder-based model. It's like a librarian. It reads the whole sentence at once, understands the context of every word from both directions, so it's fantastic for understanding and classification tasks.
And GPT?
GPT is typically a decoder-based model. It's the novelist. It reads from left to right and is optimized to predict the next word. That's why it's so good at generating coherent long-form text. And then you have models like BART that try to combine both.
Incredible. Okay, let's move away from labels entirely. What if we just have a pile of data and want to find patterns? We're now in unsupervised learning.
The goal here is just finding hidden structure. The classic algorithm is k-means. It's a clustering algorithm that tries to group your data into a predefined k number of clusters.
And it tends to find clusters that are kind of spherical, right?
Exactly, because it's based on finding a center point for each cluster. But, how do you even evaluate it when you don't have ground truth labels?
Right. How do you know if your clusters are any good?
You have to use what are called intrinsic metrics, things like the elbow method or silhouette analysis, which measure how tight the clusters are and how far apart they are from each other. But because k-means is so rigid, it fails on complex shapes.
Like the half-moon data set we saw.
For something like that, you need a different approach, like DBS scan, which is a density-based method. It can find clusters of arbitrary shapes.
Very cool. And for our final topic, learning by trial and error, reinforcement learning.
RL is all about an agent learning to make decisions to maximize a long-term reward. These problems are framed as Markov decision processes, or MDPs. Now, the key insight is that older methods, like dynamic programming, could solve these, but only if you knew the complete rules of the game.
The transition probabilities.
The exact probability of what happens when you take an action in a certain state. But in the real world, you almost never know that.
And that's where RL comes in.
Precisely. RL methods like Q-learning don't need to know the rules. The agent just interacts with the environment, tries things, sees what rewards it gets, and learns the optimal strategy through pure trial and error.
We see this implemented using toolkits like OpenAI Gym
Right.
to simulate these environments.
Yes, Gym provides all these environments, from simple grid worlds to complex games, so researchers can develop and test their RL algorithms, like Q-learning, which is probably the most popular one today.
What a journey. I mean, we started with the absolute basics, debating whether to use mean imputation for a missing value. Then we moved through sophisticated validation techniques and ended up deep inside things like generative adversarial networks and the complex architectures of transformers.
We really did span the entire spectrum, from models that are prized for being transparent, like a decision tree, to the immense black box power of a huge neural network. The whole deep dive really shows that this field isn't about finding one single best tool.
It's about a series of informed trade-offs.
Exactly, depending on your data, your goal, and your constraints.
And this raises a final provocative thought for you, the learner, to consider. We saw that feature scaling is totally irrelevant for an interpretable decision tree, yet it is absolutely critical for optimizing a deep neural network. Today, the cutting edge is dominated by these huge pre-trained models like BERT and GPT, which take our raw input and transform it into complex embeddings before they even start their main task. Knowing the fundamentals now, how should we balance the simple data prep of a decision tree against the optimization needs of a deep network? Is feature scaling the last crucial link between simple and deep machine learning, that fundamental requirement that separates one entire class of algorithms from another? We'll leave that thought with you.